Okay, everyone here. So we will start today with our class. Last time we take a look into two methods for us to deal with deadlock, which is first in our prevention. Second is our avoidance, and we look into REG and banker algorithm. Under banker algorithm, there is also another type, which is safety algorithm and resource request algorithm. So last time we are until here only. We take a look into several examples for us to look into how to apply safety algorithm and how we're going to apply the resource request algorithm. So there is a things that you need to update for the safety algorithm. If you still remember, we deal with needs, which is equivalent to work. And for resource request algorithm, we need to update three things, which is availables, allocation, and needs. So there is a several example last time. Okay, one of this is this one, which is under our safety algorithm. You need to remember all the steps, and then we're going to apply it into a situation to see the solution, whether our sequence of processes is correct or not, which is to avoid deadlock. So we will check one by one until we can find out basically what is the flow of our processor to be in a safe state. When we are in the safe state, means that there is no deadlock at all. And then after that, we have a resource request algorithm. We still have several steps, and you can see here we need to update three values, which is availables, allocation, and also need. And then we will continue check using a safety algorithm to check the flow. You can see here, okay, this one not. This one just to see the sequence, whether this one is in a safe sequence or not. And then we have a request. Following the request process, which process will take into account? If let's say it is P1, so we will directly proceed to P1 first. And of course, this value will be compared with the available and also a request. Request will be compared with the availables and also request and need. To check whether you this P1, if it requests certain amount. Actually, let's say you are here, you can have the allocation, which is about the total budget that you can have, your maximum loan that you can take. So need and availables, all of these can relate with the banker algorithm. You need to relate also. So let's say P1 request RM 30,000. So is this amount can be proceed to give to P3? So it will check following this first requirement. If it is fulfill this, then you can execute the resource request algorithm step by step for you to update three value: available, allocation, and lastly the needs. So you're going to update all the value into the table of P1. After that, you're going to continue. You can see here, you're going to continue with the safety algorithm to check your work which is equal to availability and compare whether your needs less or equal to work. Then you're going to follow the sequence to check your flow. Is the flow that might be given previously, because we look into the previous example, if the sequence is correct, might be it is enough for your bank to support all these 5 people to have their loan, then it's going to be in a safe mode, safe state, and then after that there is no deadlock. So you can see there is a several example we take a look into. Now today we're going to directly go to the deadlock detection. Under deadlock detection, we still meet RAG. And after that, there is another one which is deadlock detection algorithm. So this deadlock safety algorithm, this deadlock detection algorithm, it's quite similar with the safety algorithm. So what is the purpose for you to learn the deadlock detection? Deadlock detection allows system to enter deadlock state. Previously, prevention and avoidance. These two algo will guarantee, these two algorithms will guarantee you to not even meet with deadlock. Okay, with deadlock. But when you are going to deadlock detection, this algorithm allow you to meet the deadlock state. So you can enter the deadlock state because you want to detect whether you have the deadlock or not. Okay, so detection algorithm also can be divided into when you are having only single instances for the resources. Last time you remember, if you are having one instances, you can only entertain or assist one process only. If you have several, it is depend on how many instances that you have. If you have 2, you can be on or be hold by 2 processor. If you have 3, you can have hold by 3 processor. Not processor, sorry, process. Okay. So multiple instances for resource type. And this is 2 scheme under deadlock detection, RAG, and deadlock detection algorithm. So as it's mentioned, it is also cover the resource allocation graph. You still remember the earlier class we deal with our RAG? We are learning on how to draw this symbol. What is this representation? So from here, you will also go deeper to this detection. Okay, please make sure you are using the resource allocation graph. Last time you already learned how to draw. So deadlock can be detected by build the RAG. So you need to know how to draw this, but then you're going to convert it to weight for graph. Weight for graph. So from here RAG, last time you learned in your previous and early state for your module 7. By using this RAG graph, you're going to convert it to the weight for graph. So remember weight. Remember weight, it means that request. Okay, you request, so you need to wait. Wait for another process who hold the resources. Wait for process who hold the resources. Okay, so here you can see node are processes. PI, if you look into like this, it means that PI request from PJ. But in our detection, we mention here as a waiting. Actually, it's similar, which is, I give you example for this state. Okay, for this state, let me try to draw here P1. And we have here R1 and P2. Okay, by looking at this is our RAG drawings. We know this is request. This is whole. Okay, so this is request, this is whole, mean assignment H, request H. Still remember assignment S, request S. P1 requests R1, but R1 hold by P2. That is the general information you still remember last time. But to use the weight for graph, you're going to know that this P1 waiting P2 to finish. Okay, when P2 finish, then this R1 will be whole and on by P1. That's why it's mentioned P1 wait for P2. So you can directly draw this wait for graph like this. This means P1 wait P2 to finish. If P2 finish, I will get whatever I own. Similar also might be used, you like, there is one girl that you really like, but this girl couple with another boy. So what you wait for? You're going to wait for them to broke up. So they will broke up, and then you said, okay, when this girl broke up with her boyfriend, so I can on her. Similar also in the process. So you wait for what? You wait for this boy. Similar also, P1 will wait for P2. So you can see here from this bigger graph, you can convert it directly to this small responding wait for graph. So here, similar also for this part. For this part, it is represent for here. What else we can have here? Now P2 wait for P5. P2 wait for P5. And then we have here P2 wait for P3. Then we have another, which is P3 wait for P4. P3 wait for P4. And lastly, we have what color? We have P4 wait for P1. So it is here. So you need to know how to represent from this RAG to wait for. It's easier, I guess, so you know how to draw. So converting a RAG to wait for graph. This is as a basic things for you to look into the deadlock detection. So maintain a wait for graph predically involve an algorithm that search the cycle in the graph. So you can use this wait for and look into cycle. Actually, you can also use the RAG, but this is like a simpler version, so it's easier for you to look into. Is that if there is a cycle, then exists a deadlock. An algorithm to detect a cycle in graph requires an algorithm of n to n power of 2 operation. So where n is the number of vertical in the graph. But for this case here, you need to check also the resource. Is there is many instances, multiple instances, or a single instances only. So here, under several or multiple instances, because just now for RAG normally it is only for single instances. Similar also on your prevention, not prevention, for your avoidance. So in several or multiple instances resource type, you're going to look into N and P. So it's just in terms of symbol. You use a different symbol rather than last time we have numbers of process like P1 and number of resource we are using R. So here N represent numbers of processes, M represent as resource. So you can see you have availables. Availables mean vector of length M. If available, J equal to K, then K instances of resource type J are J available. So K is instances. So allocation, you need to learn on metric. And lastly, request. So this is all come out for you to look into actually when you are play around with money, might be it's near to our daily activities. It's much better for you to understand. And again, you can see here, when you are having a multiple instances, you're going to apply the deadlock detection algorithm, and it's already mentioned it's quite similar to safety algorithm. And safety algorithm is quite easy. You need to remember the step and what value you're going to compare, then you're going to directly apply. So let's see our detection algorithm. So you have 4 steps also similar to your safety algorithm, but in terms of the units is slightly different. So work and finish will be the vector of M and N. You need to compare work and availability. Similar, if you look back on your safety algorithm, okay, in your safety algorithm, you're going to compare also work and work with available. So you can see also you are having altogether 4 steps. Similar with our method here. Work equal to availability. Then you're going to find an index I chessboard. So you're going to look also here. Still, but you can see you are using a request. You look into the request value and compare with your work. And you need to update the work value and continue back as usual, looping until you finish. Okay, let's see the example given. I forgot the value in our previous example. Might be it's same, might be it's different. But you can see we also have 5 processes here. And it gives you the values of instances for the resource. So you're going to have 7 for A, B is 2, C is 6. So might be you can try to draw so you can familiar with drawing because your THE take home exam normally is going to be in terms of drawing or explanation sentences. Okay, this is 7 for R1. And then we have RA, RB, RC. Here will be 2 instances and another one will be 3. So from here, you can try to draw your RAG. You can try to draw your weight 4. So for you to see clearly in terms of the allocation request and available. So this is the table that given. It gives you sequence. So will result in finish equal to true for all I. Let's see, is it this is a in terms of safe state or not. So you're going to check and you're going to detect whether the deadlock occur or not. Okay, let's see directly one by one. Start with this example. So you have the allocation and also request. Request already given in your table. So it gives you also the flow here. P0, P2, P3, P1, P4. This is the step for you to remember. Let's see the first step. We're going to compare the work equivalent to availability, which is this will be your work now. You're going to compare with request. So first our PO, isn't it? P0. So you look into okay, first of all, you're going to look the allocation. Is it all equal to 0 or not? For the allocation. When you check here, all is full. Then it's okay. You're going to see whether it is a false or not. Next, of course, step number 2. So first, we're going to look and compare the availability with the P0. P0 for the request. So you compare request and availability. Is it similar or less? Yes, you can see it's similar. So you directly go to the step number 3. You're going to update the new work. So let's see what is the answer. So this is the new work. You're going to update the new work availables. You continue with the flow given. So is it true or not? Yes, because it's meet the this condition just now. So you're going to go to the step 2 again. So next, we're going to compare just now. The flow is P0, P2. But you're going to check one by one. We're going to look into P1. P1, is it the value less or equal to your new work? What is the value of new work? I forgot already. 0, 1, 0. 0, 1, 0, 2, 0, 2. You check this one. Of course, this is much bigger. So it is false. So you continue to next process. So next process, you compare similar the request and the value of the work. It is correct. That's why you're going to continue with this work plus allocation. Then you update the work value. Finish. Then you're going to check the condition. It's going to put that finish P2 equal to true for the step number 3 here. After that, we directly go to our P3. Okay, this true supposedly here, okay? Another one later on, it will be the last one. So just now, our P2 is the true. True supposedly here. This one still not yet finished. Because just now, it did not meet this condition, okay? Then, next step, we're going to compare the P3 now. P2 is already done. P0 is already done. We look into P3. Compare the value 1, 0, 0 with 3, 1, 3. I guess it is meet the condition. That's why we're going to do the work plus allocation. Update the new value. And P3 equal to true. So you update here. Okay, you update this here. Then you go to the next. Similar also with your safety algorithm. You go to the next, you have P4. Similar, you're going to compare this value with your new work. It meet the condition, you update the work plus allocation. This is your new update of your work. This is going to be true. And this done, this done, this done, this done. There is another one which is P1. You go back and do it again. Okay, you continue again and compare the value now. This you compare with the new work. Yes, it meet the condition. You're going to update the value and now this will be true. So that will be happen. So what is the flow? This one is okay. For this one, this is a new P2 request one addition instances of type C. What is this? Not okay. So you can see here, this is all meet the condition. You check whether this all meet the initial P0, P2, P3, P1, P4. Just now P0, P2, P3, P4, and then go to the P1. All condition already true. So you check the value back whether what is the request value. And if let's say P2 requests one additional instances at C, so you add another one. Just now it is all correct, no deadlock happen. And if let's say there is another additional condition, P2 now add another request. So state of a system, the system is in the deadlock state. Why? So you need to check actually one by one, similar of just now. Can reclaim resource held by the P0 but insufficient resource to fulfill other process requests. Because you can see your P1, where is it? P2. Okay, because P2 supposedly it is 0, 0, 0. But if you add another, it's going to be insufficient. But still, you need to check and look into one by one. So deadlock exists consisting of process P1, P2, P3, P4. How to check here? Of course, you're going to do one by one. Look whether it is a meet the true or false there. So if false for some, then it's going to be a deadlock. So the sequence, the flow here is give, there is no deadlock, but when you follow and look into back, if there is another request here, so if it is not meet condition, it's going to be deadlock. Let's say you try to request and look into now P2 is request, you're going to start here first. See whether the flow is correct or not. If your first one meets, you compare because this is the first value and you meet with the availables. Availables for us is 0, 0, 0. Of course, directly, you're going to see there will be a deadlock. Because when you compare the first step, you look back here, when you compare work equal to availability, when directly it didn't meet the condition, not this. If you compare this request less or equal to work, if it did not meet condition, then it's going to be a deadlock. That is how you detect. Just now, we check the flow first, then it's okay. But when there is another additional request, you try to start P2 request. You check first, request with availability. It's not meet condition, you cannot support this request. Seems that like might be P2 want to request RM 10,000, but your bank are having RM 5,000 only. So you can see this loan is too big and your bank cannot support. That's why it cannot happen, or it's going to be a deadlock later on. So let's check here. Detection algorithm usage. So where you're going to use and how. So if deadlock is detected, we must abort. So you're going to roll back some of the processes involved the deadlock. So need to decide when or how often to invoke the deadlock detection algorithm, which depend on how often deadlock is likely to occur, how many processes will be need to roll back, which is one of it is one for each disjoint cycle. And again, if you also detect deadlock, if detect algorithm is invoked, so there are many cycle in our resource graph, and so we will not be able to tell which of the many deadlock cause deadlock. So here, just now, when we have the process termination, when we have a process termination, abort all deadlock processes, abort one process at time until the deadlock cycle is eliminated. In which order should we choose to abort? Priority of process, how long process has compute and how much longer to completions, resource for the process has used, resource process need to complete, how many process, and process interactive or page. So this is all the things that you need to consider when you detect of deadlock. So you need to consider to abort, to stop, to terminate your process or the process flow. So this is the condition for you to abort and terminate. And after you already detect, after you try to terminate it, you can also you're going to recover from the deadlock. So for recover from deadlock, resource preemption, selecting a victim, minimize cost, rollback, which is return to the same safe state, restart process for the state. Just similar also like our safety algorithm. We check one by one. If let's say it is not meet the condition of the flow, we check another process. And starvation, same process may always be picked as a victim, include number of rollback in cost factor. So the summary of all, a deadlock state occur when two or more processes are waiting indefinitely. I guess this one you can also conclude by yourself how to find out the deadlock, because last time we looked into how many example about deadlock. So there is a three principal method for dealing with deadlock, which is use some protocol to prevent or avoid a deadlock, allow system to enter deadlock, detect it, then recover. Lastly, you're going to ignore the problem altogether and pretend that deadlock never occurred. So that is on our module 7. Because that work is quite interested, especially when you are having a lot of steps just to check whether you are in a safe state or not. If you are following, like might be I want to directly doing a process for P2 and then P0 and then P3 and then P4 and back to P1. Is it correct or not for the safe flow and etc. So you can try to deal with all the step by step. Okay, any question? We finished our module 7 already. After this, we're going to take a 5-minute break and then we're going to continue with our module 8. Where's my module 8? So module 8 means that we are in correct I think, but maybe we try to finish module 8 by this week also, and next week we can start with module 9. Okay, class, if no question, we break 5 minutes and we continue, okay?
Can you share module 8 as well?
Already done. Refresh your e-learning.
Okay.
Okay. Okay, class, let me continue. I guess some of you already continue to scan the QR code. We're going to continue with our new module I already shares in your e-learning. We're going to continue with modules 8. So under module 8, we will look into memory management strategy. I guess until like module 8 and then continue module 9, 10, 11, 12. It is more near to your daily activities. You use a lot of things and it's much more easier. I guess so because if compared to like module I guess module 10 and 11, it is about file directory. So trusting is very easy because you always use it, especially in directory. How you play around with directory, how you're going to manage with your files and etc. But before we go directly deeper to all those things, we will need to manage our memory first. The things might be for your computer, you did not have enough space and etc. So you will play around with this management. You need to manage your memory by yourself. Sometimes if let's say you are having one apa tak keluar pin. Okay, let's say you are having 160 gigabyte in your computer. Sometimes you cannot use all. You don't know how. Sometimes you said, yeah, I already cleaned up all my things in my computer. I already cleaned up all my things in my handphone. But still, you can see that there is a lot of free space back in your computer, but you cannot use. So here, in this module 8, you're going to see there is several type. Okay, there is several type on a memory type of memory, and you need to manage it. You need to change how, if let's say you already have a fixed memory, I give example just a general one. Let's say in your memory you already have a partition. Maybe partition A, you on 50 gigabytes. And then partition B, you have 50 gigabyte also, and left is 60 bit. You can only allocate one partition with one process, P1, P2, P3, let's say. If you have another P4, let's say P1 only 30 gigabyte, P2 only 10 gigabyte, P3 only 10 gigabyte also. So you have a lot of other balance space. Let's say here you have 20 gigabyte left, right? Here 40 gigabyte balance and another one is 50 gigabytes. But P4 cannot even use this space because might be your managements of your memory are having a fixed partitions space. That's why you cannot. So you're going to learn. Sometimes you can combine this all together and allocate to another process. So here is the things what you're going to go through and learn into your module 8. So let's see what we're going to have. We can see that we are having a background, swapping, memory allocation, continuous and non-contiguous and non-contiguous. Oh, wow. So the objective of module 8 is to provide a detailed describe various ways of organizing memory hardware, to discuss various memory management techniques, including paging and segmentation. So this is the introduction, what you need to look into. Program must be brought from this into memory and placed within a process for it to run. Main memory register are only stored in CPU, can access directly. Memory unit only sees stream data, read address, address data, and write request. So maybe you can try to read all these things. This is just information about you before you go deeper to here. Okay, let's say you have a pair of base register and limit register defined in your logical address space. So you already allocate it. Let's say you are having process 1, process 2, process 3. So you will be given with the starting or the base register address. And then you are given with the size. So you have a size. So you know, okay, this space for this address are for process 1. For this certain amount of address, process 2 and etc. So you have a base. This is the initial one, base or start address, and the limit. Limits means also the size or until which address that you can put. So this is a base and limit register on your logical address space. And there are two types of address, which is logical address and physical address. So logical address is address generated by your CPU, and you can also know it as a virtual address. While physical address is address seen by memory unit. So logical address is the set of logical address generated by program, while physical address space is set of the physical address generated by a program. So let's see what is the things that CPU will generate. What is the things that your memory will generate. Memory management unit. So under your memory management unit, you're going to generate the physical address, while your CPU will generate the logical address. And it is all will be placed on your physical memory. So what is under your memory management unit or MMU? It is a hardware device that will help you in mapping virtual physical address. So there will be several methods after this you're going to use to allocate a process into your physical address. So many methods possible. To start, consider simple scheme where the value of relocate register is added to address generated by user process at time is sent to memory. So you have to think here, base register called as a relocation register, and another one is MS-DOS on Intel 66. 86 use the for relocation register. The user program deal with logical address. It never sees to a real physical address. So let's see the example directly. When your CPU have the logical address with these addresses 00346, and it will pass to your MMU, memory management unit. So here you're going to try to relocate the register. So this is the generated physical address later on, and it's going to share it to the memory. So this is just a basic, and that's why after this, lastly, this is the only things that you're going to see. For the generated one, you cannot see basically because it's generated by CPU or MMU, and lastly, you see, okay, it is starting here and might be following the size that also give in terms of the limits. So in terms of swiping, you're going to also try to swap any memory, and you're going to see that you have a backing store for you to putting your process. Let's say here you are having your main memory. Maybe the process one is too big. So rather than you can give to directly go to the main memory, you will swap it to your, we can secondary memory, or we call as a backing store. You swap here as waiting. So you wait until your main memory having a space to allocate this process. If there is a process that ready, which is in a ready queue, this is all the in a ready queue. If let's say this process is ready and the size at your main memory is enough, and it's going to swap in back. But this one is just the introduction for you to see how the flow is basically from your CPU to the backing store. Why you swap in and why you swipe up is all depend on the size of your memory, main memory, and also the techniques for your CPU here. So after this, we're going to look into memory allocation for you to put into the process. Just now you see there is a need for you to swipe in and swipe up. So inside here, to manage your storage in your main memory, there are two types, which is contiguous and non-contiguous. So under contiguous, each process is contained in single contiguous section of memory. So let's say you are having here, just now you have a main memory, you already have, as mentioned here, section, or similar to partition. So you have already on a section, and your section is mentioned only single process. Means that every section, if you have section 1, section 2, section 3, section 4, you only can allocate process 1, process 2. So one process in one section. So that is under contiguous. And for non-contiguous, each process is contained on non-sequential locations of memory. So might be you're going to play around with the process value. It said that non-sequential. So you're going to play around with the process also, might be. We look into it after this. But first, we're going to go deeper on contiguous. So what else the differentiation? There is several method. For contiguous, we look into the fixed partition, and another one is dynamic or variables partition. And for contiguous, we have paging and segmentation. Now let's take a look into contiguous memory allocation. Here is the things that you're going to manage. See, before that, you're going to look into problem. Problem if you are using contiguous in your CPU management. If you are having a contiguous and you are using a fixed, let's say you have a fixed size partition. So here, if the example available, you only have 1, 2, 3, 4 segment. And if let's say you are having job 1, job 3, job 4, job 2, why there is no job 3? Maybe job 3 size might be 30 kilo. That's why you can see you cannot put it here, you cannot put it here. Might be it depend on also size. So that is the things that you need to learn in this fixed size partition. So each partition may contain exactly one process only. Just now I already informed, one partition or one section only, one process. And then you can see the degree of multi-program is limited by a number of partition, but it requires protection of job memory space and also job size with the partition size. Let's see example here. You were given with these 4 jobs. Altogether 4 job here. You have job 1, job 2, job 3, job 4. Let's say this is the CPU memory that you have. This is memory that you have. You have partition 1 until partition 4. And stick in your mind, it fixed. You cannot change it to be 50K, cannot change it to be 60K, it's fixed. Okay, and the contiguous type of memory, maybe your laptop is like this. Then you were given with this list of process. So look at the process 1 first. So process 1 will enter your main memory. And by using the fixed size partition under contiguous, you're going to first available partition for the required size. You look into this first process, and whatever first partition that can allocate 30K, you're going to go into it. Okay, first question. Partition 1. Is the available partition size is enough for this? Yes, because we are having here 100K and our request is only 30K. So I put here job 1 is at partition 1. So totally no other job can enter. So we are having an occupied 30K. We have 70K balance. Okay, so 70K free space. Can see that? Another job coming in, basically it is in a parallel time. Job 2, 50K, and using this first available partition of required size, I check partition 1, I cannot enter because it's on now by job 1. Although the size or free size is enough to support me, I cannot. Because still remember, our contiguous only allow only one partition for one process. So I go to the next. I check partition 2. Partition 2 is 25K. It is not enough to support 50K. I go to partition 3, still not enough. And lastly, I go to partition 4, 50K. Okay, it is enough. So now it's on by job 2. Is occupy all space. Then it's okay. For job 3 now. Job 3, I have 30K. Partition 1, I cannot enter although there is another space because it's already on by job 1. I go to the partition 2, 25K, it is not enough. I go to the partition B, it is not enough. That's why I need to wait. Okay, I need to wait for another partition to be free. For job 4, it is 25K. I go to the partition 1, cannot because owned by job 1. I go to partition 2, okay, it is enough for 25K. That's why here all allocation will be at job 1, 30K. I have free space here, 70K. We call this free space in this use partition, as internal fragmentation. Internal fragmentation means that it is used by a job or process, but there is another internal free space here. And then we have partition 2 with the job 4. You can see it's allocate all the space 25. For the partition 3, no process or job. So it is totally free space for 25K. But we didn't call it as similar as internal fragmentation, but we call it empty partition. Why empty partition? Because this partition is not owned by any process and it is totally free. We call as empty partition. So you need to know the differentiation about the term of internal fragmentation and empty partition. Empty partition, no process, so you can allow other process to come in if the space is enough. But internal fragmentation, although it is free space, you cannot allow. While for empty partition, can allow when the size is meet the requirement. Lastly, for partition 4 is allocate for job 2 and occupy all. So this is also explanation here. But you can see here when you are using this, you lost many size here, which is supposedly you can use, isn't it? So this is a problem. And another problem is when you need to wait. Your process need to wait to get a free, not a free space, but free partition. And free space for here when partition is not enough, the size is not enough. So you can see by using fixed size partition, you have a problem. You can see here the disadvantages of fixed partition, which is require contiguous loading of entire program. Job allocation method. Just now, we already see this is the job allocation method. First available partition with required size. And arbitrary particle size lead to undesired result, which is when you are having partition too small. Just now you can see here when you are having a too small. So last job have longer turnaround time, which is this job cannot enter, so you need to wait. And if partition too large, there are memory waste, which is internal fragment will happen. So this is all the problem when you are using a fixed size partition. That's why you need to know how to manage. If your computer, if your laptop are using this contiguous memory allocation type and you are using a fixed size partition, you are having a problem. That's why later on you need to come out and solve the problem. But before that, we look into a example when you are having a fixed size partition. Let's say here, you were given with a new job in order job P, job Q, job R, and lastly job S. need to be allocated in the fixed partition as in this figure. Label all the job with partition each will be allocated. So supposedly it gives you the initial value. Supposedly it having a the initial. Now it's already directly provide with you, but might be we can see here how many size for partition 1, partition 2, partition 3, partition 4, 5, 6 and 7. You can see here for partition 1 you have altogether 20k, means that job P is 20k also, it's allocate all. You can see here. Partition 2 having a 5k, partition 3 10k, partition Q 20k, but the partition 4 actually you have altogether 25k because you are having the internal fragment. And then partition 5 5k, partition 10k, and lastly partition 7 you are having 35k. So here actually it is a similar thing because it didn't give you the initial partition with empty value. But later on we're going to look into another example for you to see actually how you're going to allocate it, which is going to also similar with your dynamic variable partition. So here, let's see the dynamic variables of partition. Just now you see in terms of, okay, let me show you. Let's say in the beginning, you don't have any of this. Let's say we are having in the beginning, I draw you directly. This is your OS, P1. You have P2, 20k, P3, P0, P1, P2, 5k. We try to put and meet this solution. Before this is the initial, okay? We try to come up until here. So you can see the process. Here will be P3, 10k, P4, 25k, P5, 5k, P6, 10k, and lastly 35k. Okay, here you are having P job P 20k, and as you remember, you are using a first available partition with required size. This is how you are going to use the fixed size partition. So here 20. So I check for my P1 first. Okay, the size is meet. Okay, I'm going to sit here. That's why you get like this. Job P. Altogether 20k. Allocate to all. There is no internal fragmentation. For job Q. For job Q here, I have 15k. I will double check all the one by one. I check here cannot because it's owned by job P. I check another one. 5k cannot because it's too small. I check another one. Cannot also because it's too small from 15k. I check another one. 25k. Okay. Enough for me. I'm going to go for this size. Although it is a this size is 15k. You can see here 15k, but altogether supposedly here is 20k. Okay, I don't know the initial value because it doesn't mention, or maybe this is the initial value. So I put here 30, 20. So I can see here, it is enough for me. I'm going to tag my Q here at the partition 4. But because it is 20K, I have only 15.5K to use. Another 5K will be the internal fragmentation. So here will be 5K, here will be 15K. So I done for the job Q. Now I go for another job, which is job R. Or job R is 10K. I'm going to check one by one again. P4 cannot because there is a job P. P2 cannot, it is too small. P3, okay, it is totally fit to my request. So I will put job R into partition 3. Lastly, job S. Job S nak guna warna apa? Hitam. So job S here is 25K. I check one by one. Cannot here because that is job P. Cannot here, it is too small. Cannot here, there is job R. Cannot here, it is job Q. Here too small. Here too small. And lastly, the last partition is 30 and it meet the requirement of 25 here. I just want to use 25. So I have another 5K balance, which called as internal fragmentation. So this is contiguous fixed size partition method. So this is how actually you allocate and you get this answer. So you have a problem for this because there is a lot of empty space here you cannot use. And it also took time when you need to check one by one. So is it okay? Any question for this method? We're going to look into next one, which is still under contiguous dynamic variable partition. For dynamic variable partition, you will use slightly different terms. Different term, which is when you are having internal fragmentation, we call it as a whole. Whole block of available memory, holes of variable size are scattered throughout memory. So when a process arrives, it allocates memory from a hole large enough to accommodate it. So this is the way for you to put in. But we can see the example later on. Process existing frees the partition, adjacent free partition will combine, or when process terminate, it will release the partition. So it's going to merge its adjacent partition if any exists. So you can see here you are having operating system maintain information about allocate the partition and a free partition, which is called as a whole. So here you can see the example. Initially you are having like this. You have 3 partition. All are equipped with the process. But now you can see at the second step here, let's say your process 8 finished. So this will be your free space for you to allocate any process there. Then after that, you can see there is a process 9. You can put it inside. But you can see in the same fragment, you can also put another process in as long as you have enough size to support. Let's see what is happened basically. Example 2, when you are having a job like this. A, B, C at the T0. T1, you are having EF. T2, we are having G and H. For the dynamic variable partition, we use the terms of first come, first serve. So here, first of all, we are having A, B, C, D, and first we're going to look into A. But it didn't give me the initial one. Initial job entry memory allocation. It didn't give me anything, which is because it is like a one partition at initial. If you have 150k, so all together are 150k. But it is depend on the first allocation. Okay, this is all the step by step that you need to know. Okay, this is the solution. First of all, you're going to fit with the job A. Job A will make a partition like this. Just now, initially it's empty, okay? It's empty means that if you have 200k, then it's going to be 200k. And when there is a job A, you're going to allocate only 10k. You have the balance of 190k. So this shows that this first process make a partition of 10k. Another one is 15k. This job B make a partition of 15k. Let's see the example here. So number 2 will making a 15k here. Number 3 will make 20k, and lastly 50k making another partition. So you can see that at the initial, you already allocate with the 4 partition. At the time T1, job A will finish and job D also will finish. Okay, in the condition given, in the question, it mentioned job A and job D finish at T1. Assume that this is T1. And at the T1 also, later on you can see, when it's finished, it will make you a hole. It will left you a hole. Job D finish, job A finish, it will left you a hole there. And you can see new job coming in with each E and F. So E is 5k, you're going to go for this selection. There is a hole there, you can get E like this. So it making another partition. So you have another 5k. For job F, of course, you're going to look into the size. Here is available, so you're going to make 30k, 20k. Next, if let's say at the T2, job C finish. Just now, job C is here at 20k. So when the job C finish, it has a whole of 20k. And when you have T2 also, there is a new job will be coming in. So check this first come first serve. G will be go first. So it will check the size also. All the size, it is not enough, this is enough. So that's why you're going to go here. So job G will be here. While for the H, it is not enough for any all of this whole. That's why you need to wait. Waiting for job F to finish. So you cannot enter. So job H has to wait, even though you can see if you add them together also, you have the enough space. Free space between partition of accommodate, but you need to wait because you cannot combine them together. It's already become a partition. So that will be also a problem for you when you use the dynamic partition. Let's see another problem here. When we are having P and Q. Oh, okay. Initially, this is all the process or job that you are having initially. Then, is it similar to previous? No. Then, you need to, it's mentioned at T1. After this, T1, P, and Q will be finished. So, what happened? Wow, besarnya. So, here it will be 20K empty space. Here will be empty space for 5K. Job R is still there. Job Q will be empty, 15K, 20K empty, 25 and 5. Here will be job S. It's mentioned that new job arrived at T3, which is, this is a new job. So what happened? This T will be looking into inside here. Is there any enough space? No, you need to wait. Similar also U, 35. But for V here, you can try to look into which is the empty space. So you can see at the T1, P and Q finish. Or might be this one is the one partition just now. So it is a P and Q finish. So T0, T will be look into the size, cannot, here got a process and here is enough. So you're going to go for this because this is first come first serve. And then for you need to wait because there is no space left. And for V here, you can see after that you go to the V. V is enough for this size. So that's why it's enter here. So job T and Q has entered. Job U need to wait. So based on the example just now here, job H and U respectively have to wait until job N with enough size. So the disadvantages produced through a block of available memory hole with different size scattered out the memory. So this will be a very critical problem also. That's why from all this problem, you will look into a solution. And the solution is going to reallocate your dynamic partition. So all these empty or fragment, internal fragment here, or we call as also a hole, we're going to reallocate it. Where you're going to reallocate? You're going to reallocate at one place. So if you want to place it here, all will be putting here and they're going to combine them together. So let's see. There are two types of fragmentation. Internal fragmentation just now, and also internal and external fragmentation. Internal fragmentation when we are using and find in the fixed partition allocation, while external you use the dynamic variable partition allocation. So that's why later on you're going to use this thing and you can combine them. So solution for you, to reduce fragmentation is deallocation. Free allocate memory space. So you're going to have reset status job, and another one merging and compatible compactions of dynamic partition. Fixed partition are using a reset status job. And we call this port is as allocation dynamic partition. So it is easier for you to see when you try to look into to request. Your CPU will revert back with 0 or 1. 0 mean free, you can enter, 1 mean busy. And let's see the example directly. You are having the list of job here. And you have the first initial. Let me draw the initial first so that it's we can relate with the question. Initial, we are having partition 1, 28K. Partition 2, 32K. Partition 3, 30K. Partition, sorry, wait, here will be on the job P2. P2 here, 30, 62. And after that, we have job 2, which 16K. And here will be P4, P5. P5, 48. And lastly, I don't know. Maybe it give you directly the total size, not total. Okay, ni total of free size. It didn't give you the size all. It's okay. So this is quite the initial one, and you're going to look into how you're going to allocate. First job, first come, first serve. 8K when you go directly for P1, it is enough. That's why totally you're going to use the 8K here. 8K, and you have this free space of, wait, let me calculate the free space. 12, 12 plus 8, 20K. Okay, because I don't know the initial value, okay? But this is how you're going to put inside. So here will be the job 1. Job 2, you look into one by one. So for this side, for job 2, maybe for this part, why it is enough, not enough, I don't know. Might be there is something else that initially it's not enough. And job 3 here, it is a 32K. So you're going to put here, somewhere here, 32K. And then for job 5, it's going to be at this side. 1, 2, 3, 4. Supposedly it's here, 48K. And another one is 84K is waiting. So let's say you are having all together here, and you already allocate into your initial space just now. Supposedly it's going to give you, maybe I don't calculate it correctly. And you can see here, when you are having these terms, you're going to get like this. Ya Allah, where is my pen? Okay, so you're going to get like this. and you are having a balance of all the external fragment or holes. Using the deallocation, you're going to take all this empty space and you're going to put at one location. Merge and combine the holes at one location. So you're going to combine it all here. Following the size, you add the size together, you're going to get 96K. So that's why you can see after you already do the deallocation. So after you already deallocate, you can continue and put inside here. And still you are having a balance. So this is how you're going to occupy the deallocation, which is by combine all the free space or external fragmentation, and another one is the whole. Combine them together and you can allocate enough space for another program. So let's say example here, at initial is give you 3 jobs, snapshot A until 6, or snapshot of A until 6, and you are having all this job here. Job B, E, F, and H. Before and after you compact it. When you already put inside here, and this is waiting, this is how it look like initially. And you are having the free space here, free space here, free space here. What you need to do, you need to combine them and put into one location. When you are having this, you already merge and put in one location. This size is enough for the H just now that width. So you can allocate it to the H and you still have a free space balance. So this is under deallocation. It's quite easy, isn't it? So you have another exercise. Maybe we can try to do it another one more time. Okay, job V and R finish. How jobs you can enter the memory. So what you need to do, you try to combine them together first. You're going to get free space of 1520K. So after 20K, if job V and R finish, sorry, this one also finish, V and R, you have another 25, 45. Here will be 45, and because of this, you combine all the free space, okay, and also the job that finish. This you can enter. You still have another 5K balance. So let's see the answer. It didn't give you answer. So just now you can do it. How you do? By using the deallocation methods. So reallocation methods for you, you're going to combine all the holes, all the external or internal fragment. You combine them and you have a quite many balance. You're going to put into the partition. So similar also this exercise, so you can try to do it. So initially it's already give you like this, following the size that needed. Okay, any question? But you can see here, yet although you think that okay, now I have a solution, I can use these reallocatables dynamic partition for me to use all the free space, but still it have a problem whereby use How to satisfy requirement of size n from the list of free holes. So use the placement algorithm by selecting the free blocks memory. There is another placement algorithm: first fit, next fit, best fit, and worst fit. So you need to check the detail. What is the first fit? What is the best fit? What is the next fit? And lastly, worst fit. So all of this, we're going to look into the example and how all the algorithm will be used by next class. Is it okay? Any question until up here? This is all the applications from the method. If you know the method, you understand the method, it's easier for you because it's just an easy logic things. You can just combine them together and you have many free space and you can use it for any program or a job.
Doctor,
Yes?
so supposedly if in a memory, so if a question mentioned that a certain job has finished, and then we will have free memories, right? So what if the free memory, the size of the free memory is enough for the new job to enter? So in that case, do we still need to implement the merge and combine?
Okay, it's depend also in the question what method that they ask you to do. But you can for the THE, if the question asks you what you need later on, are you going to use the methods of reallocation? If you need to justify, you said okay, after the job for, let's say, leave, right? Just now you mentioned, right? So you have a free space, so it is enough for another job to coming in to use that space. So it is no need for you to use the relocation. Unless, let's say, it is still not enough, then you need to justify. So you are the one need to justify what method that you are need to use, or might be in the equation it will be given for you directly. Okay, you need to use the reallocation. Please explain.
Okay, understood.
Okay, so if there is no direct methods that asked in the question, so you are the one that need to justify, because THE, it is your need to explain by yourself. Okay, any other question? Okay, if there is no question, later on we're going to go with another algorithm. Still, it's easy because you can see directly and apply into your knowledge to your own laptop size, space for your main memory, how you're going to apply it. And you can see here for first fit, you're going to allocate the first hole that big enough. But all of these four methods are different. So you're going to use, maybe later on, similar also your friend asked me just now, might be not only for the reallocation, might be you can also been given with the question, okay, which one from this method, there is an example here. Okay, for this exercise, you can see here, determine which partition each request will be allocate for the following. So you can be also asked in your final exam, you need to check one by one. Okay, by using which algorithm, which will give you, let's say, a huge or a big free balance space, or might be which will occur a waiting for, let's say, process 3, which will be occur waiting for process 2. So you need to know all this algorithm and know how to explain. Okay, so I guess if there is no question, we can end up our class, and might be you can try to look into other slide first, because it is not too much more. there is only few things. We can finish our next class, and later on we're going to continue with module 9. I guess this is all not hard, only that you need to know how to explain in THE type of question. Okay? So thank you, class. Stay safe. Meet you again next Wednesday. On Wednesday. Wednesday, right?
Tuesday.
Tuesday.
Tuesday,
Sorry.
Rata.
Okay.
Tuesday, yeah, Tuesday. Thank you, Rata.
Okay. Bye bye.